Today I am going to discuss about the continuous charge distribution. And now, if you place some charges on a point, okay, now this point is considered as a point charge. Similarly, if you place charges on a thin wire, we cannot consider it as a point charge. It means the distribution of charge, it may be one dimension, or it may be three dimension, or it may be three dimension. Two dimension means if the charges are placed on a surface, it is considered as a surface or surface charge density. That's why this distribution of charge is divided into three types. It may be one dimension, it may be two dimension, or it may be three dimension. Okay, therefore there are three types of charge distribution. One is a linear charge distribution or linear charge density. It is denoted by the letter lambda. It can also defined as, or it can also said to be line charge density or linear charge density. What it means? Now, if you place some charges on a thin wire, those charges are distributed over the surface of the wire. Okay, here this distribution of charge is known as linear charge density. It can be defined as lambda is charge per unit length. Suppose if its length is L, then the total charge is Q and length is L. Therefore, the charge per unit length is nothing but linear charge density. Now here, this is the length of the wire. You are placing some charges on this wire. Okay. Therefore, lambda is equals to Q by L, and its SI unit is, see, Q is equals to, or Q, the SI unit of the Q is coulomb, and length, that is meter. Therefore, the SI unit is coulomb per meter. And let us take one example here. Now I am taking a ring and its radius is R. Okay, and I am placing some charges on this ring. The total charge is Q. Therefore, the linear charge density, that lambda, is the total charge Q and the length of the ring is L. Here this Q is a charge. The Q divided by the total charge, the total length. The total length is nothing but the circumference of the circle. The circumference of the circle is 2 pi r. Therefore, lambda is equals to Q divided by 2 pi r. This is the linear charge density of the ring. Okay. Now similarly, one more type, that is surface charge density. The surface charge density is denoted by the letter sigma. And now, instead of the wire, now I am taking a sheet. On this sheet, I am placing some charges like this. Okay, the total area is A. The area of the sheet is A. Okay, now the surface charge density can be defined as sigma is equals to the total charge by the total area A. Means it is defined as charge per unit area. Here I am considering a length, here I am considering area, because this thin sheet is having area A. Therefore, sigma is equals to Q divided by A. Now what is the SI unit of this? Q is nothing but in coulomb and area is in meter square. Therefore, the SI unit is coulomb per meter square. Okay. Now here also we can take one example, that is take circular, or take one sphere. On this sphere now a spherical conductor. Now place as charges. Now how to define the surface charge density? Sigma is equals to the total charge is Q and the total area A. Now Q divided by what is area? Area of the sphere, that is 4 pi r square, where r is the radius of the sphere. Now you can see here that the charge Q is uniformly distributed over the surface of the spherical conductor. Now this is a spherical conductor. On this sphere we are placing some charges. That charge is Q. Therefore the surface charge density sigma is Q divided by 4 pi r square. This 4 pi r square is the surface area of the spherical conductor. Now similarly one more type, that is volume charge density. In volume charge density, the total charge is distributed over entire volume. Now this is 1 Q. If you place some charges in a Q, now here the volume charge density can be defined as, this is rho equal to charge per unit volume. The total charge, we are placing a charge Q divided by total volume is V. You can see here charge per unit volume, the total charge is Q and its volume is V. Therefore the volume charge density rho is equals to Q divided by V, and its SI unit is coulomb per meter square, because charge has SI unit is coulomb and V is meter cube. And here take one example. Consider a spherical body. Place charges. RQ is a charge distributed over entire the sphere. Now the volume charge density, the charge is Q divided by what is the volume? Volume V is 4 by 3 pi r cube, because the charge has a radius r and its volume is 4 by 3 pi r cube. Now if the charge is Q is uniformly distributed over entire volume, now this is what spherical body. The total charge is Q, or you can say small q, and its volume is V. Now what is the volume of a spherical body? That is 4 by 3 pi r cube. Therefore the volume density of charge rho equals to Q divided by 4 by 3 pi r cube. These are the three types of charge distribution, and in next class we will discuss the force and electric field due to this continuous charge distribution. Okay, thank you. Okay, and now we will discuss force and electric field due to continuous distribution of the charge. The first one, the linear distribution of charge, means the charges are distributed along a line. That is the linear distribution of charge. Okay, now here I am considering a thin wire. Its length is L. We are placing a charges, total charge Q is placed over the length of the wire. Okay, to find the electric field due to this wire. Then how to find? Okay, now I am considering a small length, that is dl. Due to this, what is the electric field at a point q naught is at a distance r12 from this one. Okay, now this dl is considered as a small length because we know already according to the Coulomb's law we can find the electric field due to a point charge. We can't get the electric field due to whole length. That's why I am considering a small length, it considered as a point charge. Therefore, this dl is negligibly small. Okay, now according to the distribution of charge, the lambda is equals to its charge is dq and the test charge, that is q naught, is at a distance r12. Therefore, lambda is equals to dq by dl. Therefore, dq is equals to lambda into dl. And now, the electric field E is equals to R. First, we take a force. The force is equals to 1 by 4 pi epsilon naught. Okay, 1 by 4 pi epsilon naught q1 q2 divided by r square. What is q1 here? This is q1. What is q2? q0 is a q2, which implies 1 by 4 pi epsilon naught q1. What is q1? dq is the q1 and q2. What is q2? q0 divided by r square. What is r12 square. Okay, this is the now here this dq is at a distance r1 from the origin, or this r1 is displacement vector, or this r1 is vector, r2 is vector here. Okay, therefore the resultant vector is r12. Now force equals to 1 by 4 pi epsilon naught. What is dq here? dq is equals to lambda into dl. Therefore, the small force act on a q naught charge due to the small charge dq is equals to df. That is a small force act on a charge q naught. That is df is equals to 1 by 4 pi epsilon naught. This is into q naught into dq by r12 square. Okay, now df is equals to, substitute dq value, dq is equals to lambda into dl. Now dq is equal to lambda into dl r12 square. Okay, now this is what a small force act on a q naught. Now I have to calculate, or now we have to calculate the total force act on q naught due to this whole length. That's why apply integration now. Just apply integration to this step. That is the total force on a q naught due to length L. F is equals to 1 by 4 pi epsilon naught q naught. This charge is q naught. Integration means due to total length. Integration over L lambda into dl divided by r12 square. This is what the total force act on a q naught or test charge due to length L. Okay, by using this we can find the electric field. How to find the electric field? E is equals to, we know already, F is equals to Q into E. By using this relation we can find electric field. E is equals to F divided by Q. Okay, F divided by Q. We know already F. F is here. F is equals to 1 by 4 pi epsilon naught Q naught lambda into dl by r12 square. Now substitute the value of F. Okay, now E is equals to F divided by Q naught. Okay, this Q naught get cancelled. What is the remaining one? 1 by 4 pi epsilon naught into integration of lambda to dl by r12 square. This q naught get cancelled with this one. Okay, now this is what expression for electric field due to the continuous charge, linear distribution of charge. Here r12 is the displacement vector. Now r1 is the position vector of dq charge and R2 is the position vector of Q naught charge. Now R12 is the resultant of these two. Means according to the triangle of vector addition, this can be written as now see here R1. Now this is arrow mark here, this is the vector and the same direction, plus R12 is equals to this is R2, or this is opposite direction, that's why I am taking my negative direction, or you can take equal to R2. Okay, now R12 can be written as R2 minus of R1. You can place R12 by R2 minus of R1. Okay, and next we can see, due to a surface distribution of charge, what is the force and electric field. Okay, now here I am considering a area a thin a sheet, it has charge q and its area is, total area is s. Okay, now due to this sheet, what is the electric field and what is the force at the point q, or what is the force act on q naught and what is the field at this point, we have to calculate now. Okay, okay, to calculate that I am considering a small area, its area is ds. Okay, due to this much charge, it has a charge only dq, small charge. Due to this charge, what is the force act on this q naught test charge. Okay, now according to the surface charge density, sigma is equals to, we know sigma is equals to charge is dq divided by area is ds, which implies dq equals to sigma into ds. Therefore the force act on a test charge q naught due to this much charge means dq charge, that is df is equals to 1 by 4 pi epsilon naught into q naught. It means q1 into q2. First one is q1 and q2. q1 is sigma into ds and q2 is q naught only. Then what is the distance between these two? That is r12 square. Okay, we know that dq is nothing but sigma into ds here. Therefore the total force act on this test charge due to this whole charge, it has charge q, whole charge is q, therefore q is the charge, total force act on a q naught, f is equals to 1 by 4 pi epsilon naught into q naught integration over s, means due to whole surface, s is equals to sigma into ds divided by r12 square. Now this is what force. By using this we can find electric field. Electric field E is equals to force per charge. Okay, force is here 1 by 4 pi epsilon into q naught sigma ds divided by r12 square, and this is q naught. This q naught get cancelled. What is the expression for electric field? E is equals to 1 by 4 pi epsilon naught. Okay, q naught get cancelled. Integration over s sigma ds divided by r12 square. Same here also r12 is the resultant vector. By using the vector law of addition, here also cancels, r12 is equals to r2 minus of r1. Okay, now this is the expression for electric field and it one is force. Okay, similarly we can find the force and electric field due to volume charge density. Now I am considering a volume V. The total charge of the volume is q. Q is the total charge and V is the volume. Okay, now to find the total electric field and to find the force and the total electric field, now I am considering a small volume is dV. Okay, now this is a small volume dV and it has a charge dq. Okay, due to this charge, what is the electric field or what is the force on q naught charge? Okay, we know force is equals to 1 by 4 pi epsilon naught q1 q2 divided by r square. But here q1 is dq and q2 is test charge, that is q naught. Okay, and dq is at a distance r1, it is a position vector, it is in this direction, and r2, this is also position vector of q2, and here r12 is in this direction. It means this charge applies a force on this one, this is test charge, positive charge, it is the repulsive direction, means this charge repulses this one, means this force is in this direction, that is r12 direction. Okay, now the small element applies a force, that is a small force dF is equals to 1 by 4 pi epsilon naught q1 q2. Okay, now this q1 is this much charge. Okay, this charge can be defined as by using the volume charge density. The volume charge density rho is equals to dq divided by this dV. Okay, here dq is equals to rho into dV. Here what is it is dq into q naught divided by r square. What is dq here? 1 by 4 pi epsilon naught. dq is rho into dV into q naught. This is test charge. R, what is the distance? R12. This is R12 square. Okay, now this is dF. And next, this is what force due to a small volume element. Now I can find the total force. The total force acts on q naught charge, that is F is equals to 1 by 4 pi epsilon naught. This is q naught integration over volume, means due to total volume V is equals to rho into dV divided by R12 square. This is R. Okay, now this is what expression of force, and by using this we can calculate electric field. Electric field is equals to force per unit charge, that is q naught charge. F by q naught, F divided by q naught get cancelled. The remaining step is 1 by 4 pi epsilon naught into integration of V rho into V divided by R12 square. Here R12 is equals to R2 minus of R1. Okay, now this is what expression for electric field, and this is the expression for force due to the volume charge density. Okay, in next class we will discuss some applications of Gauss theorem. Okay, thank you.